Welcome to day 4 of Master AI in 30 days. We've built a strong foundation, mathematical concepts on day 2, machine learning essentials on day 3. Today, we're entering the world of deep learning, the technology that's revolutionized AI over the past decade. Deep learning has enabled breakthrough achievements that seemed impossible just years ago. Computers can now recognize images better than humans, translate languages in real time, generate photorealistic images from text descriptions, and engage in natural conversations. All of this is powered by deep neural networks. Today, you'll understand what makes deep learning different from traditional machine learning. You'll learn about neural network architectures, how layers stack together to create powerful models. You'll explore convolutional neural networks for computer vision and recurrent neural networks for sequential data. You'll understand backpropagation, the algorithm that enables deep learning, and you'll discover transfer learning, the technique that makes deep learning accessible even with limited data. By the end of today, you'll grasp the core principles behind systems like ChatGPT, Stable Diffusion, and self-driving cars. You'll understand not just what deep learning can do, but how it does it. Let's dive into the deep end. Here's what we'll master today, and these concepts are the foundation of modern AI systems. First, we'll understand deep neural network architecture. What makes a network deep? How do layers stack together? What do hidden layers actually learn? We'll demystify the structure that powers everything from simple classifiers to GPT-4. Second, we'll learn backpropagation, the algorithm that makes deep learning possible. This is how networks learn from errors, adjusting millions or billions of weights to improve performance. Understanding backpropagation means understanding how training actually works. Third, we'll master convolutional neural networks. CNNs revolutionize computer vision by learning hierarchical visual features. They're why your phone can recognize faces, why autonomous cars can see, why medical imaging can detect diseases. We'll understand what makes CNNs special and how they process images. Fourth, we'll explore recurrent neural networks and their advanced variants like LSTMs. These networks handle sequential data, text, speech, time series, where order matters and context from the past influences the present. They power language models, translation systems, and speech recognition. Finally, we'll discover transfer learning, using pre-trained models as starting points. This democratizes deep learning. You don't need millions of labeled images or weeks of training time. You can leverage models trained on massive datasets and adapt them to your specific task. After today, you'll understand the architectures behind modern AI breakthroughs. Deep learning is a subset of machine learning based on artificial neural networks with multiple layers. The deep in deep learning refers to the depth of these networks. They have many layers stacked between input and output. Traditional machine learning often requires manual feature engineering. For image classification, you might manually design edge detectors, texture analyzers, and shape descriptors. The algorithm then learns to combine these handcrafted features. Deep learning is different. It learns features automatically. Early layers learn simple features like edges and colors. Middle layers combine these into more complex patterns like textures and parts. Deep layers learn high-level concepts like objects and scenes. This hierarchical learning happens automatically through training. Why did deep learning explode in the 2010s after neural networks existed since the 1980s? Three factors converged. First, we got massive data sets. ImageNet provided millions of labeled images. The internet provided billions of text examples. Second, we got powerful GPUs that could train models thousands of times faster. Third, we discovered better algorithms, improved activation functions, better optimizers, techniques to prevent problems like vanishing gradients. Deep learning excels at unstructured data, images, text, audio, video, data that doesn't fit neatly into rows and columns. Traditional machine learning struggles with this. Deep learning thrives on it. This is why deep learning dominates computer vision, natural language processing, speech recognition, and generative AI. The trade-off? Deep learning requires more data, more computation, and more expertise than traditional machine learning. But for complex problems with abundant data, it achieves unprecedented performance. Let's understand the basic architecture of neural networks. A neural network consists of layers of neurons arranged in a specific structure. The input layer receives your raw data. For an image, this might be pixel values. For text, it might be word embeddings. Each input feature becomes a neuron in this layer. There's no computation here, it's just the entry point. Hidden layers are where the magic happens. Each hidden layer transforms the data it receives, extracting progressively more abstract features. In image recognition, the first hidden layer might detect edges. The second might detect textures. The third might detect object parts like eyes or wheels. The fourth might detect whole objects. Each layer builds on what previous layers learned. The output layer produces your final predictions. For classification, you might have one neuron per class. For regression, you might have a single neuron outputting a continuous value. The output layer's activation function depends on your task. Softmax for multi-class classification, Sigmoid for binary classification, linear for regression. Fully connected layers mean every neuron in one layer connects to every neuron in the next. This creates a dense web of connections. Each connection has a weight, a number that gets multiplied with the input. During training, these weights adjust to improve predictions. The depth, number of layers, and width neurons per layer are design choices. Deeper networks can learn more complex patterns but are harder to train and risk overfitting. Wider networks have more capacity but require more computation and data. Finding the right architecture is part art, part science. Activation functions are crucial for deep learning. Without them, stacking multiple layers would be pointless. Here's why. Matrix multiplication is a linear operation. If you stack multiple linear operations, the result is still just one linear operation. No matter how many layers you add, you'd only have the power of a single layer. Activation functions introduce nonlinearity. They allow networks to learn complex, nonlinear relationships. Think of trying to separate two groups of points that are spiraled around each other. You can't do it with a straight line, you need curves. Activation functions provide those curves. ReLU, rectified linear unit, is the most popular activation function for hidden layers. It's simple. If the input is positive, output it unchanged. If it's negative, output 0. Mathematically, fx max 0x. Why is it so popular? It's computationally efficient. It helps prevent vanishing gradients, and it creates sparse activations, which improve efficiency. The downside is dying ReLU, where neurons can get stuck outputting 0, but variants like leaky ReLU address this. Sigmoid squashes inputs to a range between 0 and 1. It's S-shaped. Very negative inputs become close to 0, very positive inputs become close to 1, and 0 maps to 0.5. It's useful for the output layer when you need probabilities, but it has problems in hidden layers, mainly vanishing gradients where very large or small inputs have tiny gradients, slowing learning. Tanh, hyperbolic tangent, is similar to sigmoid, but outputs between 1 and 1 instead of 0 and 1. It's zero-centered, which can help training converge faster. Like sigmoid, it suffers from vanishing gradients for extreme values. Choosing activation functions matters. ReLU for hidden layers is usually a safe default, sigmoid or softmax for output layers when you need probabilities. Backpropagation is the algorithm that makes deep learning possible. It's how we train networks with millions or billions of parameters. Let me walk you through the process. Training has two phases, forward pass and backward pass. In the forward pass, your input data flows through the network layer by layer. Each layer performs computations, matrix multiplications, and activation functions, transforming the data until it reaches the output layer. This gives you a prediction. Next, we calculate loss, a number measuring how wrong the prediction is. For classification, this might be cross-entropy loss. For regression, mean squared error. The loss is a single number summarizing the model's mistake on this example. Here's where backpropagation comes in. We need to know how to adjust each weight to reduce the loss. With millions of weights, testing each one individually is impossible. Backpropagation efficiently computes the gradient, the direction and magnitude each weight should change for all weights simultaneously. The backward pass propagates errors from output to input. It uses the chain rule from calculus. The loss tells us how wrong the output is. We compute how each weight in the final layer contributed to that error. Then we propagate this error signal backward to earlier layers, computing each weight's contribution along the way. Once we have gradients for all weights, we update them. We nudge each weight slightly in the direction that reduces loss. The learning rate controls the size of these nudges. Repeat this millions of times over millions of examples, and the network gradually learns to make better predictions. This is gradient descent applied to neural networks. Backpropagation makes it computationally feasible for deep networks. Convolutional neural networks revolutionized computer vision. Before CNNs, image recognition was difficult and feature engineering was critical. CNNs changed everything by automatically learning hierarchical visual features. What makes CNNs special? Convolutional layers use filters, small matrices that slide across the image detecting patterns. A filter might detect vertical edges, another horizontal edges, another corners, another textures. Each filter produces a feature map showing where that pattern appears in the image. Early layers learn simple patterns like edges. Deeper layers combine these to detect more complex structures like textures, then parts, then whole objects. Here's the key insight. Filters share weights across the entire image. A vertical edge detector learned in one part of the image works everywhere. This is called translation invariance. A cat is a cat whether it's in the top left or bottom right of the image. Weight sharing dramatically reduces parameters. Instead of millions of independent weights, you have hundreds of filters each with a few dozen weights. Pooling layers reduce spatial dimensions while retaining important information. Max pooling takes the maximum value in each region, keeping the strongest activations. This provides some translation invariance and reduces computation. As you go deeper, spatial dimensions shrink, but the number of channels increases. The typical CNN architecture: input image, convolutional layer, activation, pooling, repeat several times, flatten, fully connected layers, output. Early conv layers detect low-level features on large spatial dimensions. Deep conv layers detect high-level features on small spatial dimensions. Final fully connected layers combine these features for classification. CNNs power image classification, object detection, segmentation, face recognition, medical imaging, and more. Let's dive deeper into the convolution operation itself, because understanding this is key to understanding CNNs. Imagine you have an image, a matrix of pixel values. A filter is a small matrix, maybe 3x3 or 5x5. The filter slides across the image from left to right, top to bottom. At each position, it performs element-wise multiplication between the filter values and the image values it's covering, then sums the results. This single number becomes one pixel in the feature map. For example, a 3x3 vertical edge detector might have values like 1, 0, 1 in each row. When placed over a vertical edge in the image, where pixel values transition from dark to bright, left to right, the multiplication and summation produce a large positive number. Over horizontal edges or uniform regions, it produces values close to zero. The resulting feature map highlights vertical edges. A single convolutional layer typically has dozens or hundreds of filters. Each learns a different pattern. One might detect vertical edges, another horizontal edges, another diagonal edges, another color gradients, another textures. Each filter produces its own feature map. These feature maps stack to form the layer's output. Early convolutional layers learn simple local patterns because they see small regions. As you stack layers, later ones effectively see larger regions, receptive fields, and can detect more complex patterns by combining features from earlier layers. A deep conv layer might detect eyes by combining edge and texture features from earlier layers. This hierarchical feature learning is why CNNs are so powerful. You don't manually design these features. The network learns them automatically from data. Recurrent neural networks handle sequential data where order matters and the past influences the present. Text, speech, time series, video, these are sequences where RNNs excel. The key innovation is the hidden state. Unlike feed-forward networks that process each input independently, RNNs maintain a hidden state that carries information from previous time steps. When processing a sentence word by word, the hidden state accumulates context. By the time you reach the end, the hidden state encodes information about the entire sequence. Here's how it works. At each time step, the RNN receives an input, like a word, and the previous hidden state. It combines them, applies transformations, and produces a new hidden state and an output. The same weights are used at every time step. This is weight sharing across time. The network learns to use the hidden state as memory, storing relevant information and forgetting irrelevant details. Applications are everywhere. Language modeling predicts the next word given previous words. Machine translation converts sequences in one language to another. Speech recognition converts audio sequences to text. Sentiment analysis processes text to determine emotion. Time series forecasting predicts future values based on past observations. The challenge with basic RNNs is vanishing and exploding gradients. When backpropagating through many time steps, gradients can become very small, vanishing, or very large, exploding. Vanishing gradients mean the network can't learn long-term dependencies. Information from 50 words ago gets lost. Exploding gradients cause training instability. This is why we developed more sophisticated architectures like LSTMs. LSTMs, long short-term memory networks, were designed to solve the vanishing gradient problem in RNNs. They're more complex than basic RNNs, but far more powerful for long sequences. The key innovation is the cell state, a separate pathway for information flow that runs through the entire sequence. Think of it as a highway where information can travel unchanged across many time steps. The hidden state, in contrast, is more like local roads with frequent transformations. LSTMs use gates to control information flow. Gates are neural network layers that output values between 0 and 1, determining how much information passes through. The forget gate decides what information to discard from the cell state. Maybe we're reading about a new subject and should forget information about the previous subject. The input gate decides what new information to add to the cell state. Maybe we just learned a key fact that should be remembered. The output gate decides what information from the cell state to output to the hidden state. This gated architecture allows LSTMs to maintain information over long sequences without gradients vanishing. Important information can flow through the cell state highway with minimal transformation, preserving gradients during backpropagation. Meanwhile, gates can learn to forget irrelevant information and update the cell state with new relevant information. LSTMs became the dominant architecture for sequence modeling before the transformer era. They power language models, translation systems, speech recognition, video analysis, and more. They're more complex than basic RNNs. More parameters, more computation. But the ability to handle long-term dependencies is worth it. Modern variants like GRU, Gated Recurrent Unit, simplify the LSTM architecture while maintaining similar performance. Transfer learning is one of the most practical breakthroughs in deep learning. It makes powerful models accessible even when you have limited data or computational resources. Here's the idea. Training a deep network from scratch requires massive datasets and substantial computation. Training a state-of-the-art image classifier might require millions of images and weeks of GPU training. Most people don't have access to that. Transfer learning offers an alternative. Start with a model pre-trained on a large dataset. For computer vision, ImageNet with 14 million labeled images is common. For natural language processing, models trained on billions of words from the internet. These models learned general purpose features, edge detectors, texture recognizers, semantic word relationships. These features are useful across many tasks. Now take this pre-trained model and adapt it to your specific task. Maybe you want to classify medical images but only have 5,000 examples. You can take a pre-trained ImageNet model, remove the final classification layer, add a new layer for your specific classes, and fine-tune. The early layers stay mostly unchanged. Edges are edges whether you're classifying dogs or tumors. The later layers adapt to your specific domain. Fine-tuning requires far less data than training from scratch. Those 5,000 medical images might be enough with transfer learning, whereas training from scratch would require hundreds of thousands. Training is also much faster, maybe hours instead of weeks. Transfer learning democratized deep learning. You don't need massive datasets or computational resources. You can leverage models trained by others and adapt them to your specific needs. This is how most real-world deep learning applications work today. Training deep networks requires techniques beyond basic gradient descent. Let me share the key practices that make deep learning successful. Batch normalization normalizes layer inputs during training. Each mini-batch has its inputs normalized to have mean 0 and standard deviation 1. This addresses internal covariate shift, the problem where layer inputs distribution change as earlier layers' weights update. Batch norm stabilizes training, allows higher learning rates, and acts as regularization. It's become standard in most deep architectures. Dropout randomly deactivates neurons during training. Maybe 20% or 50% of neurons have their output set to 0 for each training example. This forces the network to learn redundant representations. It can't rely on specific neurons always being active. At test time, all neurons are active, but outputs are scaled appropriately. Dropout is simple but remarkably effective at preventing overfitting. Learning rate scheduling adjusts the learning rate during training. Start with a relatively high learning rate for fast progress. As training progresses and you approach a minimum, reduce the learning rate for fine-tuning. Common schedules include step decay, reduced by factor every n epochs, exponential decay, or cyclic schedules. The right schedule can significantly improve final performance. Data augmentation artificially expands your training set by applying transformations. For images, random cropping, flipping, rotation, color jittering, scaling. For text, synonym replacement, random deletion, back translation. Each transformation creates a slightly different version of the example, forcing the model to learn invariant features. This is especially valuable when training data is limited. These techniques are what make deep learning practical. Without them, training would be unstable, overfitting would be rampant, and results would be mediocre. Let's survey landmark architectures that shaped deep learning history. Understanding these gives context for modern developments. LeNet 5, developed by Jan LeCun in 1998, was the pioneering CNN. It classified handwritten digits for check processing. The architecture was small by today's standards, a few convolutional layers, pooling fully connected layers, but it demonstrated CNN's potential. It established the basic CNN design pattern still used today. AlexNet in 2012 was the breakthrough that launched the deep learning revolution. It won the ImageNet competition with a massive performance leap, reducing error rate from 26% to 15%. Why the breakthrough? It was deeper, 8 layers, used ReLU activations, employed Dropout, and critically was trained on GPUs. AlexNet proved that deep networks with sufficient data and computation could achieve unprecedented performance. ResNet in 2015 introduced residual connections, skip connections. These allow gradients to flow directly through the network, enabling much deeper architectures. Before ResNet, networks struggled beyond 20-30 layers due to degradation and vanishing gradients. ResNet demonstrated successful 152-layer networks and spawned variants with 1,000 plus layers. Skip connections became fundamental to modern deep architectures. Transformer in 2017 revolutionized natural language processing with the attention mechanism. Unlike RNNs that process sequences sequentially, transformers process all tokens in parallel, attending to relevant context wherever it appears. This enabled much larger models and better performance. Transformers now dominate not just NLP, but are expanding to vision, audio, and multimodal domains. GPT, BERT, and modern large language models are all transformer-based. Each architecture represented a breakthrough in capability or efficiency, pushing the field forward. Deep learning has transformed numerous domains. Let's explore major application areas and their impact. Computer vision was revolutionized by CNNs. Image classification identifies what's in an image. Medical diagnosis from X-rays, quality control in manufacturing, content moderation, object detection locates and identifies multiple objects. Autonomous vehicles detecting pedestrians and cars, surveillance systems, retail inventory management. Semantic segmentation labels every pixel. Medical imaging outlining tumors, satellite imagery analysis, augmented reality. Face recognition powers security systems, phone unlocking, payment authorization. The accuracy now rivals or exceeds human performance. Natural language processing saw breakthroughs with RNNs and transformers. Machine translation converts between languages in real time. Text summarization condenses long documents. Question answering systems understand context and provide relevant answers. Sentiment analysis determines emotional tone. Chatbots and virtual assistants understand and respond to natural language. Large language models like GPT can write, reason, and code. Speech technologies enable voice assistants, Siri, Alexa, Google Assistant, real-time speech-to-text transcription, voice authentication, and text-to-speech synthesis. These combine deep learning for audio processing with NLP for language understanding. Generative AI creates new content. GANs and diffusion models generate photorealistic images from text descriptions, DAL-E, Stable Diffusion, Mid-Journey. Large language models generate human-like text, music generation, video synthesis, deepfake technology, all powered by deep learning. This raises exciting possibilities and important ethical questions. Deep learning's impact spans healthcare, finance, autonomous vehicles, entertainment, scientific research, and countless other domains. The technology continues advancing rapidly. Tomorrow is day 5, natural language processing and language models. We're going deep into the technology behind ChatGPT, translation systems, and text AI. We'll start with fundamentals, how computers represent and process text. Tokenization breaks text into units. Word embeddings map words to vectors capturing semantic meaning. Words with similar meanings have similar vectors, enabling mathematical reasoning about language. We'll explore language models, systems that predict the next word given context. This simple task, when done well at scale, enables remarkable capabilities. We'll understand how language models learn grammar, facts, reasoning patterns, and even some world knowledge. We'll take a deep dive into the transformer architecture. The attention mechanism allows models to focus on relevant context regardless of distance. This was the breakthrough that enabled modern large language models. We'll understand self-attention, multi-head attention, and how transformers process sequences in parallel. We'll study famous architectures like BERT, bidirectional encoder representations from transformers, and GPT, generative pre-trained transformer. Beard excels at understanding, question answering, sentiment analysis, named entity recognition. GPT excels at generation, writing, summarization, conversation. We'll understand their differences and appropriate use cases. Finally, we'll discuss modern large language models, the path from GPT-2 to GPT-3 to GPT-4 and beyond. What happens when you scale models to billions or trillions of parameters? What emergent capabilities appear? What are the limitations and challenges? Excellent work today. You now understand deep learning fundamentals. Tomorrow, we explore the language models transforming how humans interact with AI. See you then.